Hello, everybody. These are some basic stuff. I guess you know right now how you can ask the questions. Please do. If there's something you want to interrupt me with, go ahead. No problem. I guess you already have your 10th coffee, right? And want to go drink something. So it's very nice that the organizers put this talk at the end of the day because it's, you know, relaxing talk. There will be only like 4 equations, only up to 100 lines of assembly. So just relax. And we'll go through dark silicon and try to understand what is this about and how it relates to Java. And since you guys are tired and you know little knowledge is a dangerous thing, so I want, if you're going out of this conference or this talk with just one thing to remember, then this is it. The title was lifted from the Dr. Strangelove, right? So how I learned to stop worrying and love the bomb. And spoiler alert, for those who didn't see the film, you aren't supposed to love the bomb. It's a warning, not encouragement. So like this talk, don't try things you see here at work. Kids, please, because someone will see this vectorized code that doesn't work and they will find me and they will have questions. So try it at home. It's really, really fascinating. It's a whole new world of algorithms of different mindset. And it's great. Try it at home, but please don't do it at work. And you'll see why. So I work for a database startup company that was started more than 10 years ago by Professor Michael Stonebreaker. Is the guy who brought you databases like Ingress and Post-Ingress, also known as Postgres. And there are some information about me if someone wants to find me after. And so let's start from the beginning. At the beginning, there was a for loop. And it was, you see, state-of-the-art algorithm. You can run it on your laptop. And most of the computers, what do? They calculate hashes, they do memory access, and they do this all in for loops. So if you get this for loop, like, let's say C++, you compile it to some assembly, and you torture this GCC to not optimize it too much, because if it's optimized too much, you get a lot of assembly. So if it doesn't optimize it, this is the basic structure of the loop. So you start with comparing the loop variable with some condition, and if it's 100, then the next instruction is jump if equals, and this means that basically if the break condition is met, you jump outside of the loop. If not, you execute the body, you increase the I variable, right, and jump back to the beginning of the loop. And through the decades, processor designers tried to make this run faster. And they employ various techniques so that this code and all the other constructs are, with each generation of processors, run faster. And how do they do it? Well, typically in x86 processor or x64 processors, you get, there's a front end that will decode instruction from memory. It will convert it to micro-ops. Usually it's 1-to-1. It will issue micro-ops to backend. Backend will schedule the instructions, the micro-ops. It will track dependencies between them. It will rename the registers. It will do various stuff. It will work with branch predictor to feed information to the front end, saying where is the next instruction you need to fetch. Right? The branch predictor is very important also to actually tell the front end that the code goes that way. You need to fetch code from that part of memory. And all this was gradually improved, and there were caches introduced in various parts of the system to make it run faster, and all this required more transistors. If you have limited number of transistors, let's say 1 billion, and you want to design a processor with it, you can get to run it fast, then you can redesign it once, second time, and so on. But at some point, to make caches larger or to do it, make it run faster, you need more transistors. And throughout the decades, it worked. Basically, this plots on a logarithmic scale the complexity of chips. We started with thousands of transistors. Right now, we are in about 50 billion transistor range. And because it draws a straight line, but it's logarithmic scale, so it's exponential, right? So this is Moore's law. I guess you know it, but if you ask people, everyone has a different definition, but basically it says that every 1.5 to 2 years, something will double. Well, this something is the number of transistors on square millimeter, on a chip, the complexity of chips, however you call it, something will be double every iteration of Moore's law. This is obviously not a physical law, it's more like a marketing self-fulfilling prophecy that says this will happen, and actually companies deliver on that. But what's the issue of having more transistors? It's like with the lights, let's say LEDs on Christmas lamps. If you get every year or every 2 years, you get double the number of LEDs on Christmas lamps, it's fine. You can create better, arrange them better, but it's fine until they use too much energy. Because if you start with 100 watts, for example, that are required to power that LED chain, in 2 years, you get twice that much LEDs, and suddenly you need to spend 200 watts, then 400 watts. And well, you might say that's not a big deal, it's okay, but it's exponential. And every 2 years, you get more and more power usage out of those LEDs. So how is it that Moore's law gave us so much great processors while we're using exponentially more transistor? Well, this is Dennard scaling. Dennard scaling was defined by Robert Dennard, who was the inventor of the original DRAM chip, and he created a model of a transistor and how it behaves as it scales down. So this model is, there are some equations it defines was the static and dynamic power of transistor, but in general, he predicted that as transistors are scaled down, their power usage will go down, the frequency they can operate on will go up. So in general, everything we've seen throughout the decades that we got chips with more transistors using roughly the same amount of energy. Sometimes it went out of line, but then get back to the same trend line, and they all switched faster. But unfortunately, this is the effect that is dead. Moore's law is not necessarily dead right now, but this effect that Dennard described that gave us more transistors for free is dead, and it doesn't no longer works because as the transistors are so small, there are other effects that cause it to use energy. So in general, we cannot add more transistors to the designs that we will be able to use at the same time. So if we have a CPU and there are, like, let's say 2 epochs of the Moore's law, so in 4 years, this CPU is shrunk and occupies only 1/4 of the original chip area. So we have so much area that we can use to add bigger caches, add the bigger engines into the CPU to make that for loop run faster. The problem is that because this small CPU on the right uses the same roughly amount of energy that the CPU on the left, we cannot populate this dark part with transistors that are powered. And this is the dark silicon era. So dark silicon is the silicon that you cannot power in a CPU at the same time as everything else. and consider that it's exponential. So after 4 epochs, you basically get to that size of the CPU, and you can, in the effect, power just 7% of the area. So Michael B. Taylor was one of the first researchers into these effects, and he predicted that there will be about generally 4 results of these effects that we can see. One result would be that you can just make smaller CPUs, and that's it, right? We've seen that you can make smaller CPUs; they are nice, but this doesn't give you any advantage. It's just smaller. Maybe you spend a little less on GeeCON, but in general, there's no advantage, especially if your competitor finds a creative way to use those transistors. Then no one will buy your processors because your competitor actually found a way around that. So the other solution is to downclock those transistors. So basically, you have a chip, and some of it is not always used. Some of it is downclocked sometimes. Some of it runs on high frequency always. Do you have any, does it resemble any recent designs of processors that you might know, like the phone processors, or maybe some of the Intel processor when you have performance cores and efficient cores, right? And especially if there's a GPU built into the processor, it's clocked differently. Usually it's a very big part of the processor, and it's clocked much lower than the rest of the chip. So this is the example, right? We have M1 chip, which is old chip right now, and it's not first that had all those blocks that do some custom processing. And in effect, what happens here is we trade energy efficiency for transistor area. So we pay with transistors, creating custom segments, doing just small thing just to gain energy efficiency. So it's like when you're watching a movie, there's part of the CPU that will be working on decoding it, and not a general pipeline that is decoding it. There's if you compare something, if you maybe using SSH, there are specific instructions that are used. There are specific parts of the CPU that can be used to power that functionality. Examples, like the very obvious examples that are quite old is, for example, this instruction. This is ARM instruction that just makes a floating point to a fixed point conversion. That's mandated according to the spec of JavaScript. So this instruction was specifically designed to be used in JavaScript runtimes. Intel created an instruction that does the comparison of string comparison. So basically, if you want to compare strings, you have a special mini accelerator in CPU that does it. If it does it good, that's another question, because as far as I know, this didn't catch up in the, people didn't start using it. But in general, you have accelerators. On top level, you might think about accelerator as a GPU, but there are accelerators of many sizes. There are the blocks of CPU that does video encoding, but there are also accelerators that are represented by specific assembly instruction. If we're talking about vector accelerators, then they also occupy a significant amount of processor. This picture is, I think, it's Skylake, and you see here, this is the vector execution units. They occupy quite a significant part of the processor. So getting to actual vector registers and vector processing, what is, so we can quickly jump to the code. What is the vector register? Well, I present to you, actually, it's maybe like that. We have a register, and register is register, right? It's just some memory that is that you can access inside processor with specific instructions. Because it's memory, so it contains bits, right? So we can represent it like that. There are some buckets that contain bits, and the idea is that around these vector registers you have a bunch of accelerators that can process data that you put into those registers. So these accelerators are, what's characteristic here is that you can consider this register as a belt, conveyor belt, when you have machines working on stuff that you put there, but those machines work in a way that they work in unison. They do exactly the same thing. So there's no configurability. You can't have conditional flow, at least in basic vector instructions. You have this machinery that will execute on accord something you tell them on all those entries that you can see here. So let's, for example, let's say we have some abstract register and we can put numbers there. And we ourselves interpret it like that. We have here 8 numbers. We put them in one register, and we tell processor that these are numbers. Please consider these as numbers, let's say integers, and execute addition. And that's it. So that's one instruction, integer addition, and it's executed on all the buckets or lanes of this vector register. You get 2 registers, you execute an operation, and you get some result. So these kinds of operations you can do. There's a lot of kinds of operations that were added. If we're talking about x86, it has a long history of instruction set that were added to it to allow more and more flexibility to this processing. And sometimes when you look at those instructions, you might think that they were designed by some drunken monkeys, because they are really strange instructions and they are not very complete in the sense you think that if you can do addition or maybe bit or manipulations, this will be consistent across vector sizes, across data types, but no, there are usually some gaps in this API, in the ISA, right? So in the instruction set, which are then fixed in the next iteration of the instruction set. So before we start coding, there is a few terms that I need to know. We might have different sizes of vector registers, and this is called in Java API a shape. So there can be a shape, 64-bit shape, 128-bit shape, and so on. That's if you have a shape, which is basically a size of the vector register, you need to add to it an element type. So you might say you have element types of Java. Basically, all element types are apart from characters. So you have bytes, integers, longs, floats, and so on. And if you say that's the shape of the vector register and that's the data type, that's everything that the JVM needs to know to allow processing of that data. Because if you know the shape, like let's say 512 bits, so it's 64-byte register, and I'm operating on bytes, it means that I have 64 buckets in this register. If I'm operating on longs, which are 8 bytes, this means that there will be 8 longs in the register. Let's try some actual code. Let's see if this works. I guess it's almost there. Great. So now this runs. I hope the internet will be stable because this will be running on my server at home that contains all the vector register I want to show you. So let's do a hello world with registers. So as you can see, let's assume we have some floats to process. So let's see how we can actually load them into registers and how to process them. Because Java is a high-level language, you have very rich set of types to represent all the concepts we've seen, but it should be straightforward. So we have a float vector. Let's say vector 1. And now we want to load into this vector actual data. So it's pretty simple. We get from array. There are two ways to load data into a vector, from array or from memory segment. Memory segment is the new API. And previously, you could use byte buffers, basically on the unsafe stuff. It's no longer available. So the API was cleaned up with the view on future Java, like more cleaner Java. So that's the only two ways that you can access the data right now. So let's load floats. And so we provide an array, an index, but there's still something missing. And this is the species that I was telling you about. So actually, I need to tell JVM what to optimize for. I know that I'm running on the I have 512 bit registers, so let's see if there's a species for that. Well, yeah, there are species, and I can select specific species like for 128-bit registers, or I can use a magic constant called preferred, which means that the JVM will select it for me. So in general, when you design this algorithm, it's very important what kind of instruction set you target and what are the sizes of the vector registers. Java tries to abstract it from you in a way, and in simple cases it works, but you can't really escape from that. I will make it a constant. So we have the species. And we have this vector here. And that's how you load it. We can now load a second vector from the second array, and we can do some operation on it. So there's a ton of operations here. So there's like some basic operations have name. So if you want to add, multiply, subtract, there are special methods for that, like you would expect. There are several operations that allow you to do something more fancy that we look at later. And there are some escape hatches when you can say something like lane-wise, which means to every lane of the which means to every bucket of the vector register, please apply this operation. And there is some constant listing a lot of operations. And I guess this is the escape hatch allowing the Java folks to add new operations here. But right now, we just want to add one vector to another. And that's it. We might want to print out something so we know that it works. Let's print species information. Let's print the vector 1 and vector 2 and the sum. But we need to call this hello method first. And I have some helpers here to just generate some data for us. So let's call it and see what breaks. Okay, so it worked, and we can see here that we printed species. Species says, okay, I'm working with floats, and it's a 512-bit register, and there are 16 floats there. And here we print out the contents of the register. So actually I generated arrays that contain values from 0 to n. And you can see that this is the first register, there's second, and there's a sum that's correct. And what's nice here is this is like plain Java. You can look at the float vector, you have normal hierarchy of objects, there's some abstract vector class and so on. So basically you can also debug to it, and you can put a breakpoint here and you can inspect the contents of those objects. These are objects from the point of view of the JVM. They're not necessary objects from the point of view of the C2 optimizer. And actually, when you look at the assembly that's generated, these are very simple assembly instructions. There's no allocation of any of those objects you see here. There's just loading from memory. There's an instruction to load memory from these floats. There's an instruction to load from those floats. So and sum it. So that's basically 3 instructions. And this is how it works. Okay, let's try to do something useful with this. Sorry for that. So let's do something useful for it. There was a lot of AI talks at this conference, and they were talking about embeddings. So I guess some of you might know what are the vector embeddings of the in AI speak. So basically, they tell you how similar 2 pieces of text are. So you have 2 pieces of text, you run it through the embedding model, and you get some kind of vectors. And a lot of RAG algorithms work on that. So in order to say which of those, how close those texts in the meaning are, you take those 2 vectors and compute, you want to find the angle between them. So basically it's a dot product of those 2 vectors, and this is very simple algorithm. Basically you get a dot product of, you make a dot product of 2 vectors and divide them by their magnitude. So in terms of pure like algorithm, it's just you need to multiply elements of those 2 vectors, and under the in the denominator you need to compute the squares of each of the elements of those vectors, and then sum them up and have make a square root of that. So this is like one of the simplest things you can do with these vectors, and we can see how this works. This is called cosine similarity, and this is scalar. This is scalar implementation of this. So basically, you calculate numerator by multiplying elements of those vectors, and you have 2 terms that you need to track in denominator, which means that the below part of the fraction, and that's square of each of the vector elements. And at the end, you just do this math with square root and division. So how to do this in, well, when working with vectors? So basically, we have the species already. It's the same one as before. Let's start from, we need to start from 0, right? Because we are accumulating those values. So instead of having those floats here, we replace them with float vectors. And there's a handy method that will allow us to create an empty vector with 0 inside. We also, of course, we need to provide species. Now, let's loop through this data. Before we just loaded part of the data into vectors, now we would like to go through all the data. So it's not really complicated. And we can do something like this. Actually, well, the size of the vector is larger. And now, what we need to do, let's load. We select species, we select a vector and use this here. We have how to call that maybe vector A, and then we have vector B. And one thing to note, because these are vectors, we're advancing not by one element here, right? We are advancing by more elements. And this is also abstract based on the type and vector size. So we can ask the species to tell us the length. And that's it. Even this will run on different kinds of vector registers, sizes, and it will correctly advance through the array. So we have those two vectors, and what we have to do. So numerator is now equal. Usually we would have to do, let's copy this and see how it works. Right, so we need to multiply vector A with vector B. And now, of course, there's no overloading of operators, so we need to do add. And this is important thing. From the point of view of the API, all those vectors are immutable. So they are like value objects. And if you want to, obviously, they represent the vector registers that are mutable. And underneath, the JVM will make sure that it works nicely without any allocations if it can. But here in the API, if we do this addition, we need to store it in the original variable referencing the original vector, because otherwise it will have no effect. This is similar here. We need to do this. So this is vector A squared. Okay. And so this represents this computation, but now we are advancing every 8 or 16 variables at once, slots at once. What's interesting is that vectors have a lot of additional operations that for doing math, and this API surfaces them. So actually here you can substitute this multiply add with a special instruction which is called FMA, which is fused multiply add. The idea here is that on the assembly level, actually inside the CPU would do this fused multiply add in a sense that we're working on single precision float. It will do multiplications, and with higher precision, it will add at the same time, it will add this one value, and the result will be cast in a sense back to low precision that we're all working with, which means float, single precision. But the actual mathematical operation is more, it's faster than just adding and multiplying, and it's more accurate. So we need to, I think this works in a way that we need to do VA, FMA, VB, and add here. That's how it works. And similar here, we need to fused multiply by itself and add this vector. There are in most of those architectures there are at least 16, but usually 32 registers, and there's a lot of architectural registers, a lot more. So we don't need to worry about, overrunning the register file. We can do a lot of calculations like this without spinning to the stack. And okay, so this is the code here, and at the end we should we need to return this, right? So actually we need to return one number, and this one number can be returned by in the end we have vectors here that contain parts of the computation that's already done, and they have variable number of buckets based on architecture. So right now we would like to collapse them into one value, and this happens by doing something like numerator, and now I want to reduce lanes to one value, which is actually a surprisingly expensive operation. So I thought that this should be easy and fast, but no, it's actually this one generates a lot of assembly. So this is part of beauty of using Java, that it will not only adapt this algorithm to variable sizes of a vector register, but also provide some useful things, methods that are not necessarily one-to-one with some assembly instructions, and you have reasonable certainty that they are implemented in an efficient manner. So we have, let's say, similar with so that's our algorithm here. And let's try compiling it and making a JMH micro benchmark out of it. We'll see how it compares those two algorithms. So basically, I have some code written. So if I annotated it with my benchmark, the JMH benchmark will auto-generate itself, and this is the benchmark that was generated. It doesn't matter how it looks like, because it's just plumbing code that will try to run the code we just wrote. And so if you use the JMH, you probably recognize all this output. It just says what are the starting conditions. And now we're running this benchmark. Okay, so I think that like by default it will put in something like 10 million elements array. So it's not necessarily OpenAI based embedding vectors. It's larger, but we see the difference better then. So here it warms up and executes this method cosine similarity, which is a scalar version. There are some stats, and we see that basically it runs in 3 to 4 microseconds. And now we're running vectors. If you can read this output, you already know the answer, but we see it soon enough. So this is the scalar version, and this is the vector version. So basically, it's more than, it's almost 20 times faster. So this is the power of the vectors when they are actually used correctly, and in a sense that there's nothing that would break the JVM logic that optimizes them, and this is a pretty easy algorithm actually to implement. So if you're doing something like this, this is definitely a good way to start and do vectorization. But there are other things that you should be worried about. And since we have just 10 minutes, I will go through it without writing code. But notice that in all those examples, we were operating on arrays of floats. How often do you find yourself in your application that actually you have arrays of primitive types? Like you have 10 million of records and they are represented by longs or ints. Usually you would have some domain objects, you would have orders, clients, flights, or something like that. And if you want to apply them to vector algorithm, what would you do? I guess allocate an array, primitive array, go through your domain objects, copy the values into the array, and then run the algorithm. And you've seen that we're talking about microseconds here. So in this world, the fact that you need to allocate array or copy something, go through millions of objects to do this, it makes that those algorithms are useless. So it's very important that if you want to use those, you need to design your model, your data structures upfront just for this use, because converting data to suit this format is usually defeats the purpose. So an example is row versus column layout in databases. If you have a database table like this, which gives you, let's say these are a database of flights, you have origin, destination, airports, flight number, and so on. And if you want to do some operations on flight numbers, you want to put them into int vector, you can't easily do that. You have rows of data. Each row contains strings, contains information about carriers, and so on. And from each row, you need to pick just this one integer or even maybe short to put into a vector register. And what worse is that CPU operates on cache lines, right? So if you want to load 1 byte from somewhere from memory, CPU will take in 64 bytes that surround that 1 byte. So actually the memory traffic will be enormous. To just pick those 1 bytes, you will be transferring a lot of unnecessary data to your cache in order to pick just this one thing. So it's completely useless that way. That's why we have stuff like column databases, when data for each column is packed separately, and in that way you actually can easily, especially if you know that you want to do vector processing, you can easily just copy part of memory into the register. But in column databases, they usually employ a lot of compression schemes, because if you have data like Krakow origin airport and it repeats 10,000 times, it's much better to just store it as 10,000 times Krakow, right? There's no point in storing it in clearly. And this poses another problem for those algorithms, because if they are compressed in some way, the data is laid out nicely in columns format, but it's compressed, and if you put it into int vector, it's not necessarily ready to use. So this poses, like, you need to decide what are the trade-offs between compression and ease of decompressing and putting that data into register. And remember, if you are like modern processors can issue 32-byte loads from memory every clock cycle. So this means that usually you can fill that register every clock cycle. It has a long latency, actually. It takes a long time, but every clock cycle will allow you to issue a load from memory. And most of the time, if we're doing such algorithms like just multiplying two arrays, most of the time you will be waiting on memory. So if you run this algorithm and it's already 20 times faster, it's limited in most cases by memory access. It could run faster. What we can do, actually, we can compress data in memory, so we can bring it faster to our algorithm and then decompress it in place. Because if our algorithm, let's say it uses 10% of CPU, we have 90% of CPU, in like it's roughly, to decompress that data, and it still will run that fast. And if it's limited by memory, we might make it run faster. So it's trade-offs everywhere. Quick information about what other operations you might use on the vector registers. These are vector registers from x86 or x64. Initially, there were XMM registers. Then they were extended to be larger. So there were like first instruction were MMX. You might remember when we were all young, there were MMX. They didn't introduce new registers, but there were extensions like SSC, AVX, introduced new kinds of register, and those registers map onto each other. So actually, old register were XMM, then you got YMM, and then the ZMM. The ZMM registers are 512 bits, so that's the newest, best, and largest version of registers. And there's one great thing that comes with the newest AVX specification is mask registers. So actually there are 8 mask registers called K0 to K7 that will allow you to mask operations. So like we've seen, there were robots working on those buckets, and the mask allow us to turn them off selectively, saying no, let's say every second bucket is not active. So this is very nice. It's free. Basically, most of those instructions have a masked version. And why you would use them? For example, if you have memory that ends not as a multiple of a vector size, you have like 4 stray bytes or 4 stray integers, and you have a vector of size 8, you can load it because you will go outside of array. Maybe this will introduce segmentation fault because the memory outside that array doesn't even belong to your process. So masking can solve this. Masking can add flavors to a lot of algorithms. That's just one example. If you put a mask here, you actually can load only that part of the memory that you're interested in. And similar with stores. So actually, I don't know if loads suppress these segmentation faults, but I found that stores do. So actually, you can store data that vector to a memory that's partially not yours, as long as you mask it out. There are shuffles, which are also very important. Shuffles allow you to just rearrange the elements in the vector. So you might have some, for example, pre-compute some shuffles and know that you want to exchange specific buckets, and this will happen. And that's like the other kind of big operation that is very useful. There aren't any very general other operations. There's a lot of very specific ones that you might learn about if you want to do some specific thing. There are also gathers and scatters from memory. So basically, you can do something like this when you selectively load data by index into memory, not continuous. These are gathers, and scatters store it in memory, but it's still very, very slow compared to anything else. Important thing when you look at this code and operations is throughput and latency of the instruction. Intel has a lot of materials on this, and what does it mean? The latency is basically how long the next instruction needs to wait for the result of the instruction you're looking up. So if you're looking, you want to get a result of add instruction, add instruction has 1 cycle of latency. This means that you need to wait 1 cycle before the result of that operation will be ready. There are operations that say it's 6 cycles, or maybe there are some operations that are even longer. For example, division, like general division, is very expensive. It can be 20, 30, or 40 clock cycles. Throughput is how many such operation you can issue, and this is very interesting because the processors are superscalar, right? They can, when they process a micro-op or the operation, there are several steps they do to process them. So actually, if the instruction takes many cycles, each cycle they push the instruction to this next stage of execution, and they can take another one. So actually, even if stuff like loading from memory is slow, and let's say it takes 5 cycles to actually load data to register, if the throughput is 1, it means that every cycle you can issue another load. That's just an example. Usually it's with some arithmetic operations, but basically in order to make this work fast, you need to issue a lot of operations that they will be scheduled and sent to ports that don't conflict and that that use this superscalar architecture. So this means actually that there's no point in doing like load, add, store, and we go away to do other things. You should do this in a loop on larger amount of data, then everything will like amortize. All the costs of initially starting this will amortize. Okay, so there are sorting networks that we not talk about, which is look it up. It's really a crazy algorithm, sorting networks. And to sum it up, you need to design upfront to use this. Whether you're writing in C++ or in Java, the layout of memory for those algorithms to work is really crucial. And the algorithms are pretty complicated. As for Java, that only applies to Java, is that actually they optimize beautifully until they don't. And then there's a catastrophic cliff and all the performance goes to crap. Because if it doesn't optimize, it will allocate all those float vectors you've seen, it will allocate them on a heap as real objects and execute all the Java code you've seen, you can look up that's inside, which is crazy. It's not only not efficient, it will clear up basically. It will allocate gigabytes of data per second. So that's a big problem right now, and this is because these are real objects, right? And unless they are optimized away, these are real objects. That's why this will be a preview feature as long as there are no value objects from Valhalla. When there are value objects from Valhalla, they promise they will make this feature generally available, because the vectors then there will be value objects, and there will not be ever reified into actual fat objects. Thank you. Okay. The question is if it unloads the vector register after operation was done, or it's possible to execute main operation. It doesn't unload it. So if you create a vector object and you actually operate on it, you're pretty sure that it's there in the vector register. The only moment when it's unloaded is actually stuff like context switch, which needs to clear out the vector registers, or maybe they are just jumping to other method and there's an assembly instruction that zero outs all the vector registers. But you can assume that it's there unless you, well, it's there. Because it's very expensive, that it needs to be there and kept as long as possible.
Does this JVM do, or this is a property of the CPU actually?
No, this JVM. Because JVM issues an assembly instruction, load data from memory to this register, and unless you clear it by something else or override it, it's there, right?